Welcome to a thunderstormy day in Thailand. Yes, the rain finally did arrive, so I'm staying inside the whole day. I'm kicking off part two of the DC current sensor with CANBus project. I still don't have a snappy project name for it, but that's not going to hold me back. So as I kick this off, we're in the process of starting to make a circuit, which needs a circuit board. But what's the point of a circuit board, and how did we get to this point in the maturity of building electronic projects? Well, in the early days of vacuum tubes, when electronics really started to get going, they mounted them securely to some kind of a metal frame and then ran wires between them and soldered all the wires up. And then as transistors came into play, they were a lot smaller but much more delicate, so they needed to figure out a way to securely mount and then wire these transistors. So we went to a kind of a board situation with this wire wrap business. Now, wire wrapping was good for two things. It helped for prototyping your circuit because you could easily add and remove wires as your circuit was evolving and being debugged. But then after a while, when it was working, you just let it working, and it was in a secure room and it was well taken care of. Now, over time, they aged and wires got loose and caused problems in the circuit, so they realized it wasn't a really good permanent solution. So we moved to circuit boards, which provide two functions at once. It's a secure mechanical way to mount your components, and it has the wires built in, and it can be reproduced over and over and over quite cheaply in a factory, and hence the circuit board was born. Now, we've evolved over time in the kinds of circuit boards we're making, largely helped with the advent of computer software. Now, in my early days of circuit board layout, I did it with black tape on a glass work table with a fluorescent light shining through it, so I could see what was happening between 2 or 3 or 4 or 5 or 6 layers of the circuit, which, let me tell you, this was not an easy task. When software came about, it changed the industry, and this is where we are now. We've got circuit boards with chips that you couldn't imagine 5 years ago, incredibly dense, running at incredibly high frequencies, and they're able to manufacture them with very high quality control, and they're cheap, and it's led to really awesome products on the market. But say you want to do your own circuit board. We don't want to go back to laying things out by hand, so let's find some good software. And let me tell you, there is a lot of it out there. And with anything, of course, it comes down to your requirements. For hobbyists like me, or low volume, small product manufacturers, there's a lot of great software that's either free or very reasonably priced. And let me walk you through some of these things. The different products try to differentiate themselves by adding more features and being good at one thing or something else over the next guy. So you really can't play the game unless you can do schematic design and circuit board layout. Those things go hand in hand with all of this software. Now, you can make those tasks easier by adding things like part searching and having access to a massive library of parts that make it easy for the designer to drop a part in the schematic, drop a part into the circuit board. And then on the layout side, you can manually click from pin to pin of the different components in your system, like in the schematic, and then your tool can roll those clicks over into the circuit board, and you end up with this huge mishmash of wires that are never going to work, because as soon as you cross two wires, your circuit is going to fail. So a lot of these programs, pretty much most of them, have auto layout capabilities for the circuit board design. They'll optimally try to place and wire your components to minimize the size of the board, to minimize the number of layers of board you require, and to minimize the number of holes that need to be drilled in the board that pass a wire from one side of the board to another to avoid crossing. All of these things add up to cheaper to manufacture boards and more reliable boards and smaller boards, which lead to smaller products. So that's all good. But then on top of that, you can add things like simulating your circuit. Digital simulation of a digital circuit is fine, but where this really comes into play is simulating a circuit with analog components. This is resistors and capacitors and amplifiers and inductors and things like audio circuits, audio amplifiers, anything like this that deals with analog signals. And the software is really good at simulating these things, so you can tweak your design before you have to commit to sending something to a factory. A lot of the tools will generate a bill of materials for you, which is the short term is a BOM, a BOM. It takes all the components that you've dropped into your schematic and it produces a list of them and quantities so that you can submit this to your part supplier as a purchase order. Sometimes it will automatically just send the purchase order to a company, and a few days later a box of parts shows up. There are more sophisticated things like rules-based design tools where you can basically describe some rules of how you want your circuit built, and then it builds it for you, complying with those rules, which is important for things like the computer motherboard that's running the device that you're watching this on. No human is capable of laying out a circuit board like that by hand. And with the kinds of frequencies you're dealing with, there's a lot of rules that the industry has come to understand that make for a good or a bad circuit board layout. So you apply some rules to the layout algorithms and your circuit board becomes far more reliable. A lot of the tools have handoffs to manufacturing for things like building an enclosure that makes this board really optimally packaged. It has rules and tools in place for teamwork where you can have multiple people working on the schematic or the circuit board layout. And you can just imagine when you've got two people dropping parts into a schematic at the same time or trying to update a circuit board layout at the same time, that's when things get really tricky. And then another big thing is the auto routing and the auto layout part of the circuit board, the PC board design. The more sophisticated your algorithm is, the better the layout is, the faster the layout is, the higher speed that you can run the circuitry on that board. That's a differentiating factor because there's nothing like having a circuit board that's 6 inches by 6 inches and it takes an hour to auto route the circuit versus 10 seconds. Which engineer is going to be more productive? And you can't just throw a bigger laptop at the problem. You've got to have optimally running software to make all that work effectively. So let's jump in and take a look at a few of the pieces of software that are out there in the market. I've been reading up a lot and I've come up with a massive list of software that's available in the market. So let's just run through a few of them. I think one of the industry leaders is Eagle. It started off as a small company. It's now been bought by Autodesk, which is the company that makes AutoCAD, which is super famous in the industry. They also make the Fusion 360 tool that I use to build my 3D projects, which I print on my printer. Fusion 360, I'm barely scratching the surface of this thing. I've watched the tutorials and my mind is just blown at how powerful this software is. So I can only imagine that Eagle does the same kinds of things for you, but in the realm of schematics and circuit boards. Now, one limitation I found with Eagle is it's size restricted for the free version versus the version you have to pay for. And once you go past the free version, the price is not attractive for a hobbyist or someone, building one circuit board or two circuit boards for fun. We can move to KiCad. I think it's called KiCad. Really great program for hobbyists, and it's open source. So if you're a programmer and you see a problem or you want to add a feature, just jump right into the open source project, and it might come out in the next version if the community thinks it's good enough. You have Ultrium Designer, you have Pads, you have Express PCB, you have OrCAD, you have Allegro, and then the one I finally focused on is called Design Spark. I was attracted to it because it's provided for free by one of my parts suppliers called RS Components. I buy parts from them quite often. So they said, hey, we've got this piece of software that helps you do schematics and circuit boards, and it also ties into our online parts catalog. So that's pretty good. When you're designing your circuit board, you just say if you want to drop a new component in, you give it the RS Components part number, and bam, your part is now part of your project. But what I found after I started playing around with it is they've partnered up with another company that has a more generic part searching function, which is incredibly strong. And it's got a small piece of software that you load onto your computer that manages the downloading and handling of part specifications. And I'll show you how that works in a minute. But one problem I found, and I've actually submitted a bug report on this, is if you make your download location on a drive across your network like I do all my work on my laptop, but all my files get saved on my file server, which is another machine on the network with two massive hard disks that are automatically being backed up all the time, because that's just the way I roll. The download, the library manager app crashes if you have your downloads on a remote drive. But if you have it point to your local drive on the machine you're working on, it works fine. Now, my drive across the network is just called my Z drive or my Z drive. I've mapped it to a regular drive letter. It shouldn't be handled anything different from your C drive, but the app crashes. So that is something you need to worry about. So that means I've got to make sure I back everything up by hand onto the file server, which is not the greatest thing in the world, but it's certainly a workaround. As an update, I did hear back about my bug report, and the very helpful and friendly tech support guy responded back saying, I bet you have your web browser selected so that when a file gets downloaded, it prompts you to ask where to save it each time. And I said, yes, I do. He said, switch it to automatically saving in a certain directory every time. I made that change, and now the library loader doesn't crash. So it has to do something with the interaction of the browser prompting you where you want to save each file. And as you can see from their response, they have no intention of fixing this issue. So I guess I'll just have to live with it. But the parts searching is fantastic. The way it integrates with Design Spark is fantastic. So let's just take a look at kicking off our project and build a schematic and a circuit board layout and install our first component. Okay, here we are in Design Spark 8.1. 3 things you need to do in Design Spark: create a project, create a schematic, and create a circuit board, and they're all tied together. So the first thing we're going to do is create a project, and we browse to the directory where we want it to go. And we're going to call it DC Current Sense CANBus, just because I don't have a fancy name for it yet. Okay. Now, under this, we're going to create a schematic. using the default technology file in our open project. So in the same place, we're going to call it DC current sensor, but it's going to have the file name SCH after the end. And I'm going to save that so I get everything spelled correctly. And then back under the project, we're going to create a PC board. And it's going to go in the same place with the same name. I wish they had a way to automate that a little bit. Okay, so haven't explored the default technology thing, but I think they're going to help me with this, so I'm going to just say next. I'm only going to have a 2-layer board, but you can see it goes up to a ridiculous 14 layers. I'm going to do the mask. Well, since I'm not having this the circuit board manufactured as a complete product with all the components on it somewhere, I'm going to do it by hand. So I don't need a mask for the surface mount technology components that I'm doing. I do need a top side and a bottom side solder mask. And the auto routing is all fine. And I don't know what my board size is yet, so we're going to leave that as the default. And that's what I'm calling it. So here we are. We have a project that contains a schematic and a circuit board. So let's drop in our first component. Okay, here's where I think the power of this tool comes into play. In conjunction with the library loader, which is running, so let me just pop this up. We're going to search for parts. And you can see it's watching this directory, so I'm going to make sure I download it into the same place. So we search for parts, we pop over to my web browser, and we're going to, yeah, I know that, it's still running in the background. So we're going to search for the MCU that I'm actually using in the project. With the, if you remember, it has a sexy name, ATSAM-C21E18A. Now let's see what it finds for us. Searching, searching, and okay, here we go. So we've got, came back with 1, 2, 3, 4 entries for it. Now, this product actually comes in 2 different physical packages, TQFP and QFN. I want the TQFP version because, if I can get this to show properly, I want it to have surface mount solderable pins that stick outside the package. So this is the one I want. And if you notice, it has the ECAD model, Electronic Computer Aided Design model. If we click on this, this is where the download manager comes into play. So this is what we're going to get for our troubles. It's going to give us this schematic component, and it's going to give us this physical PC board component, which is exactly what we want. So I'm a member already, so we're going to do our download. And if you remember, we have to go to that place, personal mic PC board, circuit board components. So I'm going to save that in there. And look, we go back over to the Design Spark, and right here, sitting at the click of my mouse, is the component that we just dropped in. So there it is. Let me see if I can zoom in a little bit. Oops. Come back. So here is our schematic for the ATSAM C21E18A-AUT. I'm not worried about that extension. And if we go back over and look at the circuit board, and we click here, if we go Tools, Translate to PCB, and now we have this chip is now on my circuit board. just by a simple search. I did not have to build this. It just showed up in my search for me. Now this doesn't help me too much now because I need a lot more components in here. So let me come back to you when I've dropped the rest of the components into the schematic. So I loaded up the library wizard and proceeded to create this part. Now I found a couple of shortcomings. It wouldn't allow me to change the picture of the package, which is wrong. It wouldn't allow me to enhance the part number that ends in -SMT for the specific one I'm building. But it let me add in all of these values that came from the mechanical spec sheet on the vendor's page. And then it allowed me to enter all the functional names for the pins. But one problem was I couldn't tell it that certain pins didn't exist, like pins 2, 3, 4, and 8 don't exist in this package. And there appears to be no way to tell it, don't draw a pin here, even though I left it undefined, and it forced me to put a name in here, so I put no connection. And I've released it to the world. So I've done my contribution, and now a model exists. So I'm going to download it myself now, like anybody else can, and we're going to put it into the directory, and then hopefully the library program will load it, and here we are. We now have our voltage regulator. That's pretty cool. Okay, I just wanted to wrap up this video and show you how far I got. I spent most of yesterday getting to this point in the schematic. Searching for the components was pretty straightforward when there was an exact match, like the MCU here for our AT-SAM C21E18A. I also found the USB bridge chip, I found the CANBus transceiver, I found a USB connector, I found our 10-pin debug header, and luckily there was one for the current sensor because that's a very unusual shape. A couple of the other factors is I wanted to search for a generic red LED, but because of the way the system wants to have accurate parts so it can create a bill of materials and submit an order, it really had every single part is tied to a part number somewhere, somebody's part number, and so you can't just have generic red SMT LED or generic 10K ohm resistor. So that gets a little frustrating. Also, when I imported the LED and the resistor, I mean, if we scroll over here, I think I kept one of them. The resistor is huge. This thing is the same physical size as an IC on the board, and it takes up a lot of room in the schematic. So what I ended up doing was adjusting the model and making it much smaller, and also made the LED package much smaller. So I could do things like this in the schematic without taking a huge amount of space, because I want to have an LED indication that the 12 volt is being supplied properly and we're generating 5 volts properly. And you do that with the resistor and an LED. So I'm going to be doing that with most of the interesting things on the board, with power, with signals, CANBus traffic blinking, USB traffic blinking, all that kind of stuff. Now, having just defined the small number of wires and components I have here, let me show you what the circuit board came out to look like, because it's got this function called translate to PC board, which takes whatever you've got here and it makes a PC board. The first time it does it, it will randomly place the components either inside the board or outside as you check the little box. And it will also try to do some wiring, and basically just draws lines from point to point. Inside that, then you can run the auto router, which is supposed to put the traces on the circuit board so that it's electrically correct. But this is what I ended up with. And this is even after I manually placed a lot of the components by hand. Like I placed the 4-pin connector here on the edge of the board. This is the USB connector. I placed that. This is the voltage regulator. I knew I need the voltage regulator needed to be right next to the 12-volt input. And somewhere in here, I have my LED and resistor for 12 volts, and I have my LED and resistor for 5 volts here. This is the CANBus driver chip, which is currently connected to the 2 CANBus pins. This is the USB driver chip. This is the USB connector right there. This is the debug header. This is the MCU, and this is the current sensor. But as you take a look at this, you see all of these little text bubbles all over the place, and it makes things unreadable. Like if I'm trying to work on the circuit up here, how do I do this? I can't see the wires from all of this gibberish text in the outline of the components. But it turns out, if you go over here and you go to error, it shows you all of the errors that essentially the auto router created for itself and was unable to solve. And you click on one and it flashes. So this one is component to board, LED1 layer top. So LED1 is here. Well, yeah, I can see, I don't know why you have an error with this. It's just sitting there. It's not wired up to anything, but it's calling this a violation of the design rules because I haven't placed it or wired it up yet. That seems a little silly. Now, I have watched a bunch of YouTube videos and tutorials, and people seem to have better luck with the auto router than I have. But apparently, you can change some of the parameters for the way that the rules that the auto router follows under, like line styles and the width of the lines and the widths of the tracks and the widths of the nets and the spacings. This is apparently a big one for people to change. So I'm going to play around with that. But I have to show you one thing, and this is cool. It's got a 3D view of the layout of your board, and here's the board as it exists, even with the wires showing of the few that it was able to do and the components. So here's our 4-pin connector. This is the USB connector. It's not really lifelike, but that all comes down to how accurate the model was made for the component. I've got the power supply chip, the CANBus driver, the USB driver, the MCU, the debug header, and the current sensor, and the LEDs and resistors I haven't placed yet. Now, one thing I found the first time I ran the 3D view was the chip was too far over and it was lying halfway across the resistor and the LED. So I shoved everything over, and now it actually looks pretty nice. So I'm going to wrap it up now. I'm going to keep working on this, and in the next part I'll show you how far I got along and some more of the lessons that I learned. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.